forces to you, and the first, let's say that I have a table and I have a book on my table and it's just resting there. Okay, now let's look at what the book is, or what forces are acting on the book. Now, the book is being pulled down by gravity. You can prove to yourself that that's true by lifting up the book and dropping it. It will fall. So you know that gravity is acting on the book, and gravity will always act downward. So if I draw, now I'm going to put my free body diagram. I'm going to draw my diagram on here, okay, so that way I'm not erasing it and redrawing dots and things. But on my diagram here, I'm going to have the force of gravity pulling down. But if my book is just resting on the table, then the overall acceleration is still 0. It's not moving. That means a force must be accelerating it upward, or a force must be pushing it upward, rather. So if there's a force that is pushing it upward, we call that force the normal force, okay? We call that the normal force. Lowercase n for normal. And normal just means perpendicular to. So if my surface is flat, then my normal force is straight up, perpendicular to my surface, okay? So this is one type of force that we are going to use a lot in this course, the normal force, all right? A second type of force comes from Hooke's law, and this has to do with a spring. So let's say I attach a spring to the ceiling, and well, it doesn't even have to be to the ceiling. Let's actually say on a surface, a flat surface. All right. So let's attach an object of mass m to my spring, and let's say that I pull on my mass m and I stretch that spring out. Okay. If I let it go, it's obviously going to snap back toward the spring, toward the wall here. So what that means is that the spring must be exerting a force on the mass m, and we call that force Hooke's law, all right? And it is written as F equals negative kx, right? And k is called the spring constant. And it is simply a measure of how stretchy or not stretchy the spring is. A very large value of k means the spring is really stiff, all right? It's really hard to pull the spring. A very low k, like a slinky, means that it's very stretchable, all right? And the negative sign here, don't get too wrapped up with it. All it means is that if I stretch my spring out this way, it's going to snap back toward the direction I stretched it from, okay? That's all the negative sign means. And x is simply the distance that I stretch the spring from its original position, all right? So these are two new forces that we are going to look at over and over and over again. So let's look at an example that uses the normal force, then we'll look at an example that uses Hooke's law. So the normal force is often going to be very similar to tension if I just have something hanging. If I have something just sitting here on a desk, right, like a book, and it could be anything. This is anything sitting on a surface, okay? Anything sitting on a surface that is not falling through the surface, then this analysis holds, all right? So if I want to find what the value of the normal force is in this case, so again, I'm going to denote upward as positive, downward as negative, and I want to know what the value of my normal force is. Now in this case it's rather trivial because my normal force must be balancing my weight, and in that case I know that because my book is not accelerating. It is just sitting there. It is not moving. And if the book is not moving, then it's not accelerating. If it's not accelerating, F equals ma is equal to 0, and therefore these forces must balance. So what we can say is, without even having to go through all the steps, is that the normal force must equal the weight in this particular situation. Now, that's not always going to be the case. I can put my book on an inclined plane, and in that case, the normal force is not going to necessarily equal the weight, but it will equal part of the weight. Okay, it will balance out part of the weight. And we'll see that coming up. But this is how the normal force is applied and how it looks, all right? It is the force that is normal to the surface, all right? Now let's look at an example with Hooke's law. And let's say that I have a spring whose unstretched length is 10 centimeters. All right? Its unstretched length is 10 centimeters. And then I attach a mass of, let's just say 1 kilogram to my object, to the spring, and I stretch it. Well, now its length, let's say, is 15 centimeters, all right? So originally unstretched, it's 10 centimeters, and I pull it now so that its length is 15 centimeters, okay? And let's say that the spring constant has a value of 10. Now the units on K are a little funny. They are newtons per meter, okay? Newtons per meter. You can actually see that from F equals negative kx, right? X is going to be in meters, so K needs to be newtons per meter, so that these meters and those meters cancel out, and I'm left with newtons on both sides, all right? So there's a bit of a funny unit, but that is what the units are, all right? And I want to know what the force acting on my 1 kilogram object is. All right, so what I can do is say that F equals ma, and what I'm going to do now is look at what the force acting on my 1 kilogram object is right as I let it go, okay? Obviously, if I'm holding it, then an extra force is acting on the mass, my hand, okay? It's pulling it this way, and the spring is pulling it this way, and those two are equal and opposite. But once I release the mass, it's going to be accelerated this way, so it'll have a net force just due to the spring. So I'm going to look at the case right when the mass is let go. And this is going to be equal to, if I let it go, the only force acting on it is the spring, so this is going to be negative kx. And again, x is the distance stretched, okay? X is the distance stretched. So my spring constant is 10 newtons per meter. And how far did I stretch it? Well, its unstretched length, what we call the equilibrium length, was 10 centimeters, and I stretched it out to its until it's 15 centimeters long. That means I've stretched it a total distance of 5, right? 5 centimeters. If I want to convert that into meters, that's going to be 0.05 meters. So now I'm going to get negative 0.5 newtons, all right? Now, the negative sign's not truly important here, all right? The negative sign is not truly important here. All that means is that the force is going to be directed back toward the spring, okay? But the magnitude that it's going to move with is going to be 0.5 newtons. Now I can take this one step further and ask, what's its acceleration going to be right as I let it go, right? And from this, you should be able to see that the acceleration is not going to be constant, because as the spring gets closer and closer to its original length, x becomes smaller and smaller and smaller, and so a should get smaller and smaller as well. So this is a case where the acceleration is not constant throughout the motion. But for our purposes, we will treat it usually right as the object is released from rest. All right, so I want to know what the acceleration of my 1 kilogram object is right as it's released. So if the force is 0.5 newtons, and that equals ma, then A is going to equal 0.5 newtons divided by 1 kilogram, and that will be 0.5 meters per second squared. Now you should be able to see that if I make K stiffer and stiffer and stiffer, if I let K get larger and larger and larger, the larger this acceleration is going to be. A very stiff spring is going to snap back a lot faster than a non-stiff or a loose spring. Okay, so that is how you can use springs. I will end this video with one last example, and this example is going to kind of set the tone for a lot of the other examples that we will see. So we're going to now look at a fairly sophisticated, at least